So once in a while we talk to our clients because they have a feeling that they may need a little bit of improvement um, on their architecture, or they have the feeling that they can do more with their data. So we've spoken in the past with several clients, and one thing that started to come out common from many of the clients was that one of their main concerns was having so many duplicates. And so basically the issue is they have a large database of records, and then a new record comes in, and they need to figure out whether this is a duplicate or something else that is already in the database. And so this is, in general terms, is the problem of answering the query is record R in a database, but in general terms, any set S. This is a query. Is an object R in a set S? And in general terms, what's the simplest algorithms that we would do to solve this? Forget about what the databases are doing. How do we do this? How do we solve this query? In general, if you have a database, if you have an array instead of a database, if it was a list, how do you go about solving this, answering this query?
You iterate and compare.
Exactly. So you take the object, then you go through every single object in the set, and you look if they are the same, right? And issues with that?
Can be slow.
Yeah. So it'd be nice if someone else gets a chance to answer once in a while. So yeah, why can it be slow? Exactly. And then these records themselves could be big, like loads of columns to compare, right? Or features if these are vectors. So basically, yeah, in the worst case scenario, if you're really unlucky and the match is at the bottom of your list, you end up comparing your record with the entire database. Right, for those of you who've done Java, you guys remember hash tables, right? You know what the idea is, right? The idea is you have an arbitrary object, which is R, could be huge, made of different, a number of properties, but you can create a fingerprint of this object, and a fingerprint is just a number that represents this record. Okay, this is called a hash of record R, right? And now you can, this number, in very simplistic terms, it actually turns out or translates to a memory location, right? So that means, and then you see, you guys use PHP, so you're used to associative arrays, which are implemented using hash table. And so essentially when you have an array and you pass, say, a string here, this is actually hashed and becomes mapped to a location in memory. So you don't have to do, when you have string, you don't have to see in your database whether you have strings everywhere in your database. You essentially just get the fingerprint of string, and you can tell straight away whether it's in your memory or not, because that corresponds, it references an actual memory location. So that's fine. But if you're dealing with loads of data and very big data, having one hash may not be enough. And so a Bloom filter is essentially, it's the same idea of a hash table essentially, but you, instead of hashing your object once, you hash a number of times k, which is a parameter of the Bloom filter. And so why would you do that? Because the Bloom filter is built to minimize the number of conflicts. A conflict is when you have two objects, R1 and R2, that hash to the same thing. And this can happen depending on the hashing algorithm. And so in Bloom filter, you pick a number k of random hashing functions, and you do this to minimize the possibility of clashes between objects. And so thanks to Bloom filter, now you can ask this question very quickly. I won't go to the details, but because otherwise we lose too many times. So that's fine. And but some of our clients, they threw a little wobbler. So their problem wasn't just a duplication. The problem was that some of the records, say for example like an address for a person, you know, you could write out the same address in different ways, different abbreviations, spacing, could be referring to the same company or but different floor on the same building. And for them and for us, this record, these two records with the different way of writing the address, they would be essentially the same record, and you should keep one of them and not both of them. But for a machine implementing this, it wouldn't be the case because you're actually looking at a perfect match, right? So that was the problem. So what if the issue is not whether R is in, but whether the R is similar enough to something in S. Okay, and this is essentially as more specific version of this general problem. Okay. Now this general problem has this similar to. What does that mean? So that means that now we're talking about the idea of a measure of similarity between objects. So that's a new thing that comes into play because you can have different measures of difference or similarity between two objects depending on what you're doing. And so Jamie and I started thinking about this problem. So how do we solve this problem? How do we detect duplication where we're also concerned with similarity? Things that are similar should not be put into the database. And we both thought straight away Bloom filter, nice and easy. But as I explained before, Bloom filter are constructed to minimize the clash between items. So this means that if I have R1 and R2 and they're meant to be similar, as far as the Bloom filter is concerned, Bloom filter doesn't care that these are similar. It will construct hashes for these that are as far apart as possible in order to work the way it works. Thankfully, Jamie had heard of something called locality sensitive hashing. And what locality sensitive hashing is essentially is the opposite of what the Bloom filter is doing, because locality sensitive hashing is the idea of creating hashing function that actually maximize the probability of clashes. Okay, and specifically they think of it like this. So imagine this is the space that we're considering, right? And you have some form of distance measure. And you have a point here, which is your record, and you have another point here, S, right? And you think about anything around here, right? Anything inside here is close enough. Everything outside here is not close enough, right? So let's call this distance delta, for example. And the idea of this type of hashing is that suppose we call the function that calculates the distance, let's say we call it d. Okay? The idea is that if the distance between the 2 points, R and S, okay, is within this ball, okay, then the probability that you hash R, that the hashing of R is the same as the hashing of S is greater than some probability, P1. Okay? At the same rate, if the distance between the 2 points is greater than this ball that we consider to be close enough, similar enough, then we want the probability that the 2 hashes are the same, okay, to be less than some probability P2. We want this probability to be very high, and we want this probability to be very small. Does that make sense? Great. And it turns out you can build these hashing functions for all different measures that you care for. For example, Euclidean distance. You can have a family of these functions for cosine distance, for Hamming distance, for something called Jacquard distance when you are comparing documents and text. And so it's all well and good. And it turns out, in fact, that you can combine locality-sensitive hashing and Bloom filters to create what are called locality-sensitive Bloom filters. The idea being that if in a Bloom filter two objects, so if you find that if you hash an object and you find that all the hashes are already occupied, that means that your set has that element. In a locally sensitive Bloom filter, if one record hashes and the hashes are already occupied in the filter, that means that there exists an element in the set that is close enough, that is similar, with high probability to your object. Okay? Now, if you can look at this problem also the other way around, in a sense of how novel is what I'm looking at. So in terms of novelty, and this is where we combine computer science with flies, with fruit flies, because this problem of detecting how similar or the novelty of certain experiences and certain sensorial inputs is very important for organisms to detect what they can eat, what they can't eat, and things like that. And I found this paper while researching this, where they argue that the way that a fruit fly solved this problem, i.e. detecting the novelty of something through olfactory input, is essentially like a Bloom filter. And they went on to actually describe a Bloom filter that is very similar to how this to the strategy that the fruit fly has evolved to figure out the novelty of things. And this is roughly, very roughly, I try to explain how the fly does it, which translates to a Bloom filter. So when a sensory input comes in, an odor comes in, there are there's a bunch of neurons, okay, they will pick up this odor. And some of them will activate and some of them will not. And essentially what these neurons do, they're kind of encoding the input, the sensory input, basically hashing or tagging into, they're tagging these odors into activations of certain neurons. Okay? Then there's another area of neurons called the KC cells, which is, it stands for Kenyan cells, I hope I'm saying it right. And then usually there's like a number, say a number M of them, okay, of these cells. And what happens is this sensory input encoded here is actually projected into these cells. And this KC, this region here, becomes essentially the filter, the Bloom filter. And the way what happens, every single of these cells, strange enough, kind of encodes or integrates together randomly six of the activations of these neurons. This is just a detail. Each one of these neurons has a synapse with another big cell, which they call MBON alpha prime 3. Don't ask me what that means. And so yeah, they all form a synapses. So now what happens is an order comes in and it stimulates these cells. Okay, these cells will be integrated here. Okay, and so then that means this Kinnian cell, they will have some values now of activation and so on. And what happens is K of these, so the K cells, K is just another number, okay? The K cells that have the highest value in here, the winners, basically, the K winners have the highest values in these cells, will end up stimulating the synapses that go into this cell here. And this cell here, what it does the equivalent of looking at the novelty in terms of how many of these cells are activated. Kind of like this. If you see an order and you find out that, so say K is equal 3, okay, and you find out suppose this was 0, 0, previously we had seen something, here and here, okay? So suppose a new order comes in, right? And then we do this hashing and projection, right? And it turns out that this new order computes with this cell here, the activation would activate this cell here, and this cell here. Okay, this guy does essentially this. It looks at, okay, this one, remember K is 3, so it looks at these 3, and it says 1 out of the 3 is excited. And so the novelty is basically 1 out of 3. Or rather, it's because we're talking about novelty. So have I seen this before or not? So then you take, so it's 2 over 3. See, only 1 out of the 3 has been seen before. So this is very novel. Yes?
I lost you at the beginning of that. So
Sorry.
three of them are three of them are activated.
1 out of 3.
Three of them are activated.
Yes.
But
so this is
two
the
of them
so
have been
this is how it was before. Okay. Then you got an input. Say I'm smelling Chardonnay.
Yeah.
Right. And this Chardonnay activates these ones here.
Yeah.
You can see this one had already a 1 already. Okay. This one then this one had a 0.
Okay. So it's not that it's ever been activated before. It's just it's a change from the current activation state.
No. At the moment, we're just comparing what happened here to what the state is at the moment.
Yeah. So the state is 0, 0, 1, 0, 0, 1,
Yeah.
0, and then what's the new state is 0, 1.
No. So this when you do this projection, these 3 cells will be activated. But what happens is what this does. It does essentially. I don't know how it does it. It explains in the paper. I'm not a biologist, but what essentially happens is it looks at the activation that would be from the projection to what's in the K cells, and it looks at the only one that was there that I've seen before, right? There is an activation, matches activation is this one, okay? And it's only 1 of 3, right? If this was like this, okay, I have a signal that I've seen before.
Yeah.
Okay, does it make sense?
Yeah.
So the novelty in this case is very novel because I've only seen 1 out of the K activation, and so the novelty is 1 of the 3.
Yeah, I guess what I'm just wondering is does each new event then change the activation
Yes.
of those K cells?
Yeah. And then this is the filter. It gets updated.
Yeah.
So that there's a difference between, if you remember, there's a difference between inserting data into the filter and just processing a new input. So in a Bloom filter, you first you have your set, right? And you insert into the filter all the items in your set. But then you have, a new thing comes in. So then you need to look at, is it in the set? And then if it's not in the set, then you inject it. So this is the idea. This is before before injecting in here, you do this comparison. You check, okay, how many of the activation that would be, the case that would be activated are in common with what the state is now. It's 1 out of 3 of them. Okay. Then after you've done this, then this updates to I've seen this. So this will then become this.
Yeah. Yeah. But then you've lost the information, you've lost the previous state?
No, isn't it just the memory? Anything that's in
This is just, I have seen this.
it's not one from the net. It's just
Okay.
taking a memory.
So that's then a bank, you're building up a bank of
Yeah.
K values, KC values.
You mean a bank of?
You remember all the previous, remembers all the
So this is an encoding. It's, you remember, like the it's equivalent of the Bloom filter. You remember you had say for example a word key, and then you have k hash functions. Say suppose k is 3. That means k turns into 3 numbers. Say 1, 5, and I don't know, 5 and 6. After you've, yeah? So that means if I were to insert this into the filter, then I would have to set 1, okay, and then 1, 2, 3, 4, 5, and 6. Okay, next you see another word, right? Word. Okay, and when you do 3 hashes, you got another 3 numbers. Say for example is 0, 1, and 6. Okay, these are already set. 1 and 6 are already set, but 0 you now set. So now this filter is the same filter, updated, but now it's encoding the membership status, having seen these words. So next time if word comes in again, I hash it, I get 0, 1, 6, I see 0, 1, and 6 are taken as 1 there, so I'm saying yes, I have. Okay, cool.
Yeah.
So then I decided to reproduce the result of the paper, because the way they evaluate their what they aptly named fly Bloom filter, and it's compared with a traditional Bloom filter and with the locality sensitive Bloom filter. So it was a very nice way for me to learn how to implement these algorithms and also do a comparison. And I can explain to you how it works, the comparison, the methodology. So we can do that, but we can see here, the idea is this. So they tested this with different data sets. I just picked one of them. The data set I use is called SIFT. SIFT is basically a database of images that have been vectorized. So this is an image that is turned into 121 numbers. Okay, and then we use this algorithm to detect the novelty. The way it works is that you take the data sets, okay, you divide it into test and training. Okay, the training set you put into the filter, and then the test set. Each vector in the test set becomes your query. So you take the first one and say, what's the novelty of this with respect to the set? Okay. And so what you do is you compute the actual. So they use cosine distance. Okay. So if I have, if my test query was t, okay. And the database of the rest, the training set is S. What they would do, they would find the closest, so they're using cosine distance. And so you take this one, and in the set you actually calculate the long way, which one is the closest element using cosine distance, okay? And say it's t prime, okay? The novelty, according to the paper, would be the cosine distance between t and t prime. Yeah? So every time I'm going through an element of the test set, I do this calculation, okay? This is the true value of novelty, okay? and then you look at the results that the filters give you instead. All right. And so say you suppose the filter give you, the result ft. And what we look in here, they look at the correlation between these two values. Okay, so when you input different test queries, you'll see you'll see the distance increase and then decrease and then go there. You get something like this. Yeah. So this is the distance between the next query point and the closest item in the set, right? So this distance will change.
Yeah.
Okay. And once you look at the result of the filter, what the filter says about the same query, you also get something like this. What we want to find out is whether these two are correlated.
For each of your test inputs, how close is it to the closest of your training inputs?
Yeah.
Yeah.
Yeah. And the filter you ask,
Yeah.
what's the novelty of if I put this? What's the filter tells me how close this is? And so what they're looking at is the correlation of these two data points, in the sense that what you want is if this goes up, and this must go up, and this goes down, this should be down. You can't really compare them other than we're doing the right thing. If two things are distant, according to the true distance measure, they should look distant also from the point of view of the filter. So that's basically what they're doing, looking at the correlation. And what they're doing, they're looking at the correlation between the ground truth and what the filter tells you across different, as I said, k, you remember k is the number of hashing functions that you use, and that's a parameter of the filter, so they've done different tests across different values of hashing functions. And so you can see blue filter is pretty shitty, and it's to be expected because the blue filter only looks at equality. Really has no idea. You lose any sense of closeness with the blue filter. So it's obvious that we're not doing very well with the red one. Then the locality sensitive blue filter is doing a lot better at it. You can see there we get as close as almost 40% correlation. It's not super great, but it's definitely better than the blue filter. And then the fly blue filter is doing almost over 50% when we have 50 hashing functions, which is an interesting result. It's pretty good. And so yeah, I just wanted to show you this. All the code is we have a repo called algorithms in Bitbucket. All the code is in there if you want to have a look and understand a little bit better how these three algorithms work. Yeah, it was a lot of fun, and they basically the idea is to what Jamie and I were thinking was locality sensitive bloom filters, they don't really care about the data, but you can imagine you could learn from the data. So you can learn the same hashing, you can learn hashing functions that have the same result, i.e. they keep the similarity idea, but you can learn them directly from the data. So that's a different approach to this idea of solving the similarity query, and it's called this is called locality preserving in the literature, locality preserving hashing, because it's actually the hashing functions are learned from the data directly. And so the idea is that I wanted to experiment is, you remember I implemented this generative adversarial networks to generate probability distributions, right? And I was thinking of using them to learn hashing functions that preserve similarity out of data, and yeah, turn into some kind of product that we could sell in order to detect similarities that should be discarded when entering data into a database, basically. that's the idea why we started looking at this. That's it.
Yeah. But so on your example of addresses, where your hash functions are turning these addresses into a number to store at one of these things. But what have you got? Have you got examples of functions that you would use in that case?
Yeah, so then it's one thing in the literature, mainly the Bloom filter it's very new, and that's something that can be maybe explored, but there are definitely locality sensitive hashing functions that are used together with, so every distance measure that you use will kind of will have its appropriate family of hashing functions, of this type of functions that work better. And when
so
you do this kind of...
The first question is, well, the distance so is the first question of what's an appropriate distance measure?
Yeah, so if you were doing that kind of thing, there are several. One that is used a lot with this one, and there are papers about the family that is appropriate for this kind of distance. When you look at documents and text, that's the way you spell Jacquard distance between strings of texts. And technically speaking, this is not a metric in the mathematical sense, but you can still use this. And there is, I think, the appropriate family of hashes. It's been coded and it's called sim hash. I think you may have heard of that. So sim hash is the algorithmic version of the family that is appropriate for this distance. And so yeah, if you have documents that you would look, or
so
text fields, you would use.
Because it's kind of it's text, but it's structured text.
Yeah, and so you can use this. But what we wanted to do is just learn that directly from the statistics of the data itself, because when you really don't have this function really, you kind of, although they're built mathematically to be the best fit for this particular distance, you really lose the idea of this particular distance metric that you're using. Whereas the way we want to do it in the locality preserving, you actually learn it by calculating this distance over and over across your data set. So you're actually using your metric as the foundation of learning hashing functions, whereas here is usually lost.